Hi everyone. We're going to start straight away by showing a short clip.
Turn on outside light.
Affirmative. Turning on outside light.
What is the status of garage side door?
Garage side door is currently locked.
Okay, show you guys that it's locked. Unlock garage side door.
Affirmative. Unlocking garage side door.
Right, so the short video that you saw is from a gentleman called Armando. We got it from YouTube. As you can guess, it's not us. The accent is quite obvious. That's his home automation system, and that's going to be the title of our talk. We're going to start talking about the home automation, slightly background, what it is in general, then move on to Z-Wave protocol in particular, which was the main topic of our research as well. We would then look at security implementation in Z-Wave protocol, and finally we would move on to how such a system can be subjected to attacks. So for those ones of you who were around yesterday, there was a talk and they mentioned how you can break in through a window. We're going to do it slightly differently. We're going to walk in through the front door like a boss. So, home automation. Just to get some sort of feedback, could you please raise your hand up if you use a home automation system? Okay, quite a few people there. And how many of you have a Z-Wave home automated system? Very nice. And so out of those ones, how many use security devices, alarms, door locks? Very good. Okay, let's see how you feel by the end of this talk. So, home automation. I wouldn't talk too much about this because I'm pretty sure that most of us are aware. So we have a central control sitting at the heart of the system. And around that we have various devices from lighting control, sensors, temperature control, entry, security, etc. And this kind of system brings in a lot of advantages. One of the biggest advantages, at least for me, is that. So I'm a couch potato. I'm sure I'm not the only one here. So I would like to sit on my couch, control everything by remote control, and enjoy it. So convenience is probably on top of the list of the advantages of an automated home. We have other things as well, like energy management, remote monitoring control, accessibility, and of course security. So all of these advantages have made smart homes very interesting for a consumer. And as a result of those, companies have been investing a lot of money, improving the technologies, introducing various protocols, etc. So just to show you some figures, the system shipments was about 1.5 million smart home systems shipped back in 2012. That's expected to rise to more than 8 million by 2017. In terms of market size, back in 2011, there was $3.4 billion, and this is only the US market. So $3.4 billion in the US, and that's going to rise to more than 5.5 billion by 2016. So it's a huge market. Again in the US, and just in 2013, it is expected that 5 million Z-Wave devices will be shipped by the end of the year. So these are just setting up a background of how important this is and how big the market is, and therefore the need for security assessment of these products. So we're going to take a quick look at how does it work and how a system is put together and how different devices interact within a Z-Wave or generally within a smart home. I'm going to hand over to Behrang to talk to us.
Thank you. Okay, so we will look into the main components of a home automation system. First of all, we have the communication protocols. Most of the today's home automation systems are based on the wireless communication. Among them, the Z-Wave and Zigbee protocols are the dominant ones. This is mostly because that they can operate in sub-gigahertz frequency range, which has better penetration rate into the building walls and the obstacles compared to Wi-Fi and Bluetooth. The other reason is that these two other protocols, Wi-Fi and Bluetooth, are more power hungry and are not suitable for small devices and resource constrained applications. We still got the old wired communication, which use the power lines in the building, and as well as the dual band communication, which uses a combination of wireless communication and wired media to form a home network. As you can see, most of the power line based protocols does not implement security. This is mostly because of the fact that they assume the attacker would need to gain physical access to the power line to actually mount some meaningful attacks. And then we have the user interface. This used to be these like these wall-mounted control panels, and in some cases they had a portable remote control, which allows you to control most of the aspect of the system if you don't have the access to the touch panel. However, this is something. This is how the smart home looks like nowadays, and you can control all aspects of this smart home from your smartphone remotely, receiving the events in the form of text messages, receiving the video feeds from your home security system, and so on. And finally, we have the different devices, sensors, and modules. These devices, the small devices, are mostly battery powered, and they each of them has a tiny Z-Wave or Zigbee radio chip running the protocol stack and allows them to communicate with the central panel as well as communicating with other devices. For instance, you can pair a motion sensor with a siren in order to activate the siren automatically in the event of any movements. So we have two of these devices here, one secure AES encrypted Z-Wave door lock and another motion sensor. As these devices gain popularity, especially in the field of home security, researchers started to look into these devices. So we had this Killer Bee framework released in 2009. Basically, is a set of tools to allow you to interact with Zigbee devices, encrypted or unencrypted devices. Then we had this DEFCON talk on X10 protocol over power lines. And then finally was the war driving kit by Travis, which was a tool allowing you to identify Zigbee devices and map those devices in your proximity. So far, you don't see any public research on Z-Wave. So why we actually started to look into this protocol? Sahand will tell you more.
So why Z-Wave? So there are these various protocols. There have been studies on other protocols that Behrang mentioned. So why we decided to look on Z-Wave in particular? Well, there are a few reasons. Back in 2012, there was a survey done by the National Association of Home Builders. And according to that survey, wireless home security is at the top of the wish list of homeowners. So that's 50% of the people surveyed, 1 out of every 2, would like a home security system in their smart home. That's a huge number. Also, according to the vendor, 80% of the US home security market is Z-Wave as well. So out of those 1 in 2, 80% of them are going to end up having a home security device powered by Z-Wave. Z-Wave itself is a proprietary protocol. You need NDA with the vendor. It's going to cost you, I think, $4,000 or $5,000 to get the basic SDK, and I think another $1,000 or $2,000 to get a compiler for that. So it's expensive. It's not possible for an ordinary security researcher or a hobbyist to go and acquire that and start experimenting with this protocol. And finally, there hasn't been any public researches that we are aware of. So we searched a lot, we couldn't find anything. So for all those reasons, we thought that, okay, this seems a very good topic for a study, trying to gain more knowledge, in-depth knowledge about how the protocol works. So I'm going to talk about the Z-Wave protocol. We're starting to get a bit technical. So first of all, the Z-Wave protocol is stacked. We have the physical layer right at the bottom. So that's the frequency, the RF frequency that it uses, about 868 meg in the EU and 950, if I'm correct, in the US. Depending on the regulation, regional regulations, they use different frequencies across the world. It can operate at various bit rates, as you can see at the bottom of the slide. On top of that, we have the transport layer, which handles the acknowledgement, retransmission, and error handling of the frames. Then we have the network layer. We have a unique 32-bit home ID, which is unique to each central controller. So that guarantees that if you have a neighbor using the same technology, there's not going to be any interference between the two homes. And then there is an 8-bit node ID, which basically is when you pair a new device into the network, that node ID is assigned to it so that you can differentiate between the various nodes. Also, the mesh topology and mesh network is handled at this layer. We have the security layer, a thin layer on top of that, and finally the application layer. One thing that the Z-Wave designers did, and it was quite nice, was that they have device-specific commands and parameters in their application layer. So that's part of the standard, and that brings in interoperability between various devices from different manufacturers, which is a good thing. But then again, it also means that if there's a vulnerability, it's going to be most probably across all of the devices. So, the physical layer, the RF configuration, we found these information from the data sheets available, publicly available on Z-Wave modules. It uses FSK modulation. For those of us who are familiar with RF technology, FSK is frequency shift keying. There are various other modulation schemes as well. Basically, say you have your data stream, which is a 9.6 or 40 kilobits per second, or the newest generation of Z-Wave is 100 kilobits per second, which is a bunch of zeros and ones, and you want to transmit that. You can't send that directly over the RF, so it needs something called the carrier wave, which is the 868 megahertz in the EU. So you have that carrier wave, and you have to somehow marry these two signals to be able to transmit it over the RF. So that's where the modulation comes in. So in FSK modulation, you transmit at a higher frequency whenever there is a 1, and at a lower frequency whenever there's a 0. That higher and lower frequencies, that's for Z-Wave, is plus minus 20 kilohertz. So as you can see in that red graph, the ones and zeros, one is more condensed, one is like slightly wider. And if you were to actually see the RF signal going around the house, that's what it will look like, the red graph at the bottom. There are other things as well. The encoding, Z-Wave uses Manchester encoding and NRZ for Manchester for 9.6, NRZ for 40 kilobits per second. So those are the information which are publicly available. But we needed a kind of device to be able to see those packets going forwards and back. So we had a look around, and we found this little cute board, which is powered by a Texas Instrument chip, a Chipcon CC1110. This chip itself is very configurable. It can support various configuration, and it works in sub-gigahertz, excuse me, sub-gigahertz RF frequencies. It supports the Z-Wave configurations that we saw on the previous slide, and it can communicate with the laptop or PC using serial communication, which makes it nice and easy to develop a tool for. Best of all, it comes with a free tool from Texas Instruments called the Smart RF Studio, which is a very powerful tool, and it was very helpful in the initial stages of this research. And not only those, it's 2 for $75. It's a bargain. So we acquired this development kit, plugged in all those values into a Smart RF tool, and as you can see, we started to see some packets there. So at first glance, they look very random. Bunch of 5s and 8s and then some random numbers. It doesn't look quite good. So what's the problem there? So in digital RF communication, we have something called preamble. The receiver doesn't have any knowledge. It's not in sync with the transmitter. They need a way to become in sync. So that's where the preamble comes in, which is an alternating series of zeros and ones, which is 5-5 or AA. Following that, then there's a sync word, because the receiver now is in sync bit-wise, but it doesn't know where the byte boundary is, where the byte to start. So it needs something called a sync word. And we didn't know the sync word for Z-Wave. So what we did, right at the end of those series of zeros and ones, at the end of the 5s or A's, we got a bunch of bytes, started shifting them to the left and right, plugging them back into the Smart RF tool, and trying to see if we can get something meaningful. It was trial and error. It didn't take long, but eventually, this is what we got. So they don't look random anymore. They look like real packets, and you can see something meaningful there. We had two controllers, which by design, they should have unique identifiers, home IDs. And we started to see actually those home IDs. When we were using the other controller, the numbers were different. So that gave us a clue that where the home ID is. Also, we got to know that, okay, so when we use this device, these numbers change, so that must be source ID, that must be destination ID. We gained a lot of information from the protocol just by looking at these packets going forward and back. The checksum, and we figured how the checksum is calculated. It was a very long process, but very rewarding and very exciting. However, in hindsight, and sometime later, we found that there was a much easier way to do that. So early in 2012, the Z-Wave designers put forward a proposal to ITU, International Telecommunication Union, to standardize the MAC layer and the PHY layer, physical layer of the protocol. This was approved and published at the end of 2012. It's ITU-T recommendation G9959, and it pretty much describes all of what we did. That was very disappointing. However, not all was lost. I mean, it wasn't a complete waste of time, because we managed to find some inconsistencies between the specification and our findings. And when we got in touch with the vendor, they actually confirmed that what we saw was correct and the spec actually was wrong, and there's going to be an updated release. So that made us feel a bit happier. So in the end, this is how a Z-Wave frame looks like. Not all of this information was from us, but we used part of the specification, our findings, and also the Open ZForce, Open Z-Wave project to put together this frame format. So we have the physical layer, MAC frame, and the application frame right at the bottom. The application frame has a command class, so it's just the way that Z-Wave works because of the interoperability. the commands for each device is known. So if you have a motion sensor like what we have there, it ought to support a series of command classes and commands. So we have all of these information now, and we have our modem. We can receive stuff. So we thought, like, let's put all of these together and create a tool. And that's how ZForce was born. ZForce is a tool that we created. It consists of a GUI as well as the firmware for the chip-on devices. And these two together make ZForce, and this is a screenshot of what ZForce looks like. Basically, it can show you the timestamp of when the packet was seen or captured, home ID, source destination, and the raw packet. It can intercept at 9.6 or 40 kilobits per second. So you have this device near a smart home which uses Z-Wave. You can see all the packets going forwards and back. And interestingly, one packet is all what an attacker would need. Using that single packet, you would know the home ID, and you as in a potential attacker, of course, I'm not implying that you would do that, but so you have that single packet, you find the home ID, and then you can probe the network, the home network, to find out all other devices and their capabilities. The source and destinations and things like that, they aren't encrypted, they aren't part of the security, so you can send raw status check to packets to all of the frames, all of the devices, and start to build a network map of what there is in that system. Once you know all the nodes in the system, then ZForce enables you to send or inject raw packets within the network. So you have complete control, and you can actually interact with the devices across the home network. So here, we're going to show you a little demo of how we use that to disable a motion sensor, which could have been used in a typical smart home.
خیلی نویز داره.
Right.
اینجا رو نشون بدی.
Which button was it?
Two. Two.
Right. So Behrang just tells me that there's a lot of noise here. Our tools are designed to work in our lab, and I'm not quite sure. It might be because of the various equipment that are here. It seems that we're seeing quite a lot of noise.
Speakers.
Yeah, we use RF mics and various other things, so that's something that could have happened.
Let's check the board.
Right, I think we probably have to skip over this one. It's a bit disappointing, but yeah, we seem to have some noise problem. So basically, I just took it through. So the motion sensor that we have here, it's actually marketed as a secure device. But what we found is that it's not actually secure. It doesn't implement any security encryption. We're not sure whether that's across the range or it's just this single one that we acquired. But what happens is that when there's a movement, this motion sensor sees the movement, sends a packet, and if things went right, we could have seen it on ZForce page. Using that, we would know the node ID of the motion sensor. And also we know there's a specific packet that is needed to actually disable or enable this motion sensor. So say, for example, you have, at your home, at night, you sleep upstairs and you disable the motion sensor upstairs. So there is, by design, there's the possibility to actually disable these motion sensors. And we know that packet, what that packet is, and ZForce can actually inject that packet. So what we're going to show you today at this demo was basically seeing some movement. The device captures those, the ZForce captures those, and then we use ZForce to send the device a packet to actually disable the motion detection. And then you can move in front of the motion sensor and nothing would happen. So that's basically your motion sensors out of the window. So we're going to move over to Z-Wave security. Some other devices, not all of them do not apply security. So some of them do, like the door lock that we can see there. So we're going to move over to Z-Wave security, and Behrang is going to talk us through.
Thank you. Okay. In order to address the issues with the clear text devices, which were subjected to the replay attack, unfortunately, we couldn't demo the motion sensor, but the problem is that as these devices just transmit over the clear text, you can just capture and replay the packets to enable or disable any functionality on them. So in order to address this issue, the Z-Wave vendor actually released the fourth generation of their radio chips, the ZM4 series, and they implemented the AES crypto engine in those chips to provide some sort of some degree of security into the protocol. There were, again, similar to the protocol specification, there were no public documentation on the security layer, the packet formats, or any other specification about the type of the algorithm used in this cryptographic operations. So we studied this new chip using our Z-Wave tool as well as some firmware analysis, and figure out that this actually it is using the 64-bit nonce values to provide message freshness in order to counter those type of message replay attacks. It uses a 128-bit network key and has two key derivation functions in order to derive two separate encryption and macking key from the network key, KN. And then the encryption algorithm used was AES algorithm, well known and respected, in output feedback mode. And for the purpose of the data origin authentication and integrity checking of the packets, they use the AES algorithm in CBC MAC mode of operation. And finally, they decided to implement a custom key establishment protocol. And this is for delivering the network key into the new Z-Wave devices. So whenever you insert a new Z-Wave device to your network, it just takes like 5 or 6 seconds for the control panel to run this protocol and deliver the new key securely to the device. So the word custom in cryptography, well, always brings up alarms. So we decided to look more into this protocol as there were no specification available. And we managed to figure out all the steps involved in this key establishment protocol, together with the type of the messages exchanged and the formulas to actually generate those packets. So what, in a typical Z-Wave key establishment, first of all, the control panels sends a knock-knock packet to a secure device like a door lock, and just informs it about the initiation of the protocol. The door lock gets back with just a ready packet to the controller, and then followed by a nonce value, 8 bytes nonce value sent to the door lock. And after receiving the nonce value from the door lock, this is the most important step of the protocol. The controller generates a random network key, KN, and then needs to deliver this securely to the door lock. However, there's no pre-shared key between these two elements right now. So they use a temporary encryption key to encrypt the new key, as well as computing the MAC. After doing this, building this secure packet, the packet is sent to the door lock verifies the received packet's integrity, decrypts it, gets the new key, which is the KN encrypted under K0. Then, if all was successful, it attempts to reply back to the control panel and tell it that it has a new key. So again, it requests a nonce value from the control panel, use that nonce value to build a secure packet. And how this secure packet is built, this time the secure packet actually is built by the KN, the new key received from the control panel. So by doing that, door lock actually proves to the control panel that it knows the key and has the key value. At the end of these protocol run, they both share the key end and can use that key to do any future secure communication, like sending back the status of door lock or getting an unlock message from the control panel. So I'm sure that some of you might have spotted the vulnerability in that protocol. And the first one is that the protocol is not based on public key cryptography, and the two entities are actually using a pre-shared key, which was that temporary key. So an attacker with access to a Z-Wave interception tool would be able to actually intercept that set key command and derive the KN out of it. However, this only happens at the system installation time. When you bought a new door lock, it just takes 5 or 6 seconds to insert it to your network. And the other measure that the Z-Waves devices use against this attack is low power transmission. When they run this protocol, they operate in low power transmission, so an attacker needs to be very close to both devices to actually be able to mount this attack. So for us, this attack was not very interesting, and we decided to look more into the protocol to derive a more meaningful attack. The second question in this, not just in this key establishment protocol, but most of the key exchange protocols, is the entity authentication. And it's simply, right now, none of these entities, the door lock or the control panel, when running this protocol, they don't know who they are actually talking to. They have no assurance that, for instance, a door lock running this protocol with the control panel doesn't know if he's actually talking to a control panel or an attacker. So the assumption of this protocol was that, well, if someone wants to run this protocol, that person should know a couple of information. So he should first know the temporary key value, which was used to actually encrypt and send the new network key, and the key derivation functions, which was later used to derive 2 other keys from the new received key. Z-Wave designers assume that these kind of information is not easy to find without access to the internal documents and internal tools. However, we managed to find this information by analyzing the radio packets as well as the firmware. So we found out that that temporary key actually is a byte array of zeros. And the key derivation functions, the two key derivation functions, one for KC for encryption key is just AES encryption in ECB mode with a password embedded into the firmware. And the key M, which is the matching key, is again the same ECB mode operation with a different password embedded into the firmware. Okay, these are the two pieces of information required to actually build that first packet. Later, we also need to know how to build encrypted packets and how to calculate the MAC value. So we figured out again that these were not available in any kind of documentation. So we did a little bit research on both the packet, radio packets and the firmware. And these are the formulas to first one to compute, to perform the encryption. So the cipher is computed over the initialization vector and the plain text. And the MAC value actually is computed this way with some parameters that you can find more details on the white paper. And then, having access to those pieces of information, we thought that maybe it's possible to mount another attack, more useful attack and practical one. So we called it key reset attack. And the idea is that as this protocol does not have any kind of entity authentication, we can pretend to be the controller, knowing those information that we derived, and run the key establishment protocol with the door lock and set our own key. Basically, the door lock will accept our key. And then, following establishing the key, we can send encrypted command this time with a key that we know, and with the MAC values we can compute using those formula to instruct the door lock to do commands like unlocking or setting PIN codes.
So that all seems that it should work, but then the question is, would it work? Because you would expect that when a secure device like the door lock has established key previously with the controller, it shouldn't accept any new keys unless we're using the same encryption key which was previously established with the controller. But that's what we found that is not the case on the product that we evaluated. So at this point, we're going to show you a live demo of how we actually attack a typical door lock which uses Z-Wave using our unauthorized reset key attack, which Behrang described. But I had to look again, and there seems to be some problems. Bear in mind that the tool that we created was more for research, so it's not robust enough to work in a high noise area like what we have in here. We have the mic, etc., and the frequency that Z-Wave uses, that's a free band, so you don't need to have to register with the authorities to use that band. It's called the ISM band. So there are many devices which operate within that band, and I'm guessing that probably our mics are using the same band or very close frequency, and that's why we're having problems. But that's not a big, it's a bit disappointing, but it's not a big problem, because just yesterday, actually, in the hotel room, just in case, we were quite sure that everything would work nicely, but we thought, let's make a short video, just in case things go wrong, and I'm really glad that we did that. Right. Sorry, that's my voiceover. You don't want to hear that, I promise you. Right, so going right to the start. So that's a, we have ZForce on the left and the door lock on the right. So what we try to do here, we launched the reset key menu, and that's what we have. We know the home ID of the device. We've probed it before, so we know the device ID as well. So we type in the home ID and device ID and just enter a random key of our choosing. So just changed ABCD in the middle and a bunch of zeros. It automatically calculates the KC and KMAC, the cipher key and the encryption key, the macking key. So here we try to send an unlock command to the door. And it shouldn't work because that's a random key that we chose just a minute ago. And it doesn't. So that's 81 where the mouse is now. That's the actual encrypted packet to tell the door to unlock. What we do next is we use the set key command, which is basically what Behrang described, and run that. So it runs through several stages, tries to establish the key, which is the key that we just created, that ABCD in the middle with the rest zeros. And the door lock confirms that's the last stage in that sequence diagram which Behrang showed. And we think that the lock should have our random key, should have established with us with that random key. So then we send an unlock command. And yes, you saw it flashing and the door unlocks. It would have been nicer if it worked live, but there you go. So, now what? In our view, that's a critical vulnerability and it needs an urgent fix. What we did here, using $75 worth of development kit and an application, it was possible to unlock that door. That could have been at my front door, at my house, or any of you guys who kept your hand up. Do you use this device, this door lock? No one's going to admit, are you? Right, so it's a critical vulnerability. That gives a potential attacker the opportunity to just walk in through the front door. They could have disabled the alarm like the demo, the first demo. So they could have disabled the alarm system, unlocked the door, walked in, and the rest I just leave it to your imagination. There can be a short-term fix, which is just to check the current key state. If the door lock would have checked that it has previously established a key with the controller, it could have stopped us to do this attack. However, there's a problem there. These are embedded devices. They are resource constrained. They aren't like a PC or a Linux box that you just patch over the air and just download a patch. It's so difficult to patch these. They do support, Z-Wave protocol does support firmware upgrade in the field. However, this lock in particular, we know that it doesn't. So if you're using that lock, there's no way for you to update it. You either have to send it back to the manufacturer, get a new one, or just accept the risk that someone might come into your house. The longest, the actual fix, which is, we believe that would be available for the next generation of Z-Wave, is a public key cryptographic and authentication, so that both the door lock and the central control can authenticate each other and know who it is that they're actually establishing key with. That would have stopped us to mount this attack as well. And just a few final words. Security by obscurity fails. We all know that. Z-Wave has been very close protocol. There hasn't been much to speak about it. Unfortunately, there hasn't been many previous work about it either. If it was an open spec, these kind of things would have been tested by security researchers a long time ago. Attacks are difficult to detect. It's not like a PC again, or a home network, or an office network. It's so difficult to detect such attacks because most of the time they don't leave any logs or any forensics. Internet of Things is not as secure yet. Again, small devices, resource constraints. They need to get away with as little power as they can, and that most of the time is in conflict with security, and we can see that in a lot of devices in the Internet of Things. Security analysis using ZForce. So ZForce hopefully is going to be available for security researchers so that they can perform security analysis like what we did and find vulnerabilities, report them back to the vendor in order to improve the security of these devices. And patching the vulnerability over the air, firmware update, which we talked about, and wisdom of the crowd. Make it open source, guys. Let everyone go and have a look and find the problems. We have more technical detail in our white paper, and as I said, the tool would be available probably in a couple of weeks' time after the Black Hat embargo. It will be available on Google Code. And that's all, folks. That's our details, the email addresses and Twitter. So you're welcome to get back in touch with us. We're now open to questions. Yes, sir. I don't know because we didn't have access to the SDK. We do query, but we didn't spend too much time on what exactly that does, the various version numbers and things like that. We are more focused on the actual attacks themselves. Well, when we reported it to the vendor, what they said that they confirmed the vulnerability. So what they told us was that they actually went through the devices, they confirmed the vulnerability does exist, and they also said that they now have mechanisms in place to actually test against this particular vulnerability. So I believe that it wasn't fixed before we reported it to them. Sure. Yeah, please, go ahead.
Okay, real quick introduction. My name is John Adams. I work with the Z-Wave group, have been involved for several years. When SensePost approached us with this flaw, we quickly identified it and we created a set of tools and test cases around it. To this date, the only identified product with this flaw is that door lock that was sold in Europe in a limited quantity, and no consumers have been affected by this flaw to date. So I just want to put this in context, that the actual flaw in the product was the application not sticking to the security specification, and it actually allowed the key to be reset. That is not as part of the specification process. So, yeah.
Thank you. Although as a consumer, because we actually bought this lock as well, so as a consumer we were probably affected, but yes, sir.
How do we know that other devices are they tested?
I believe, as Sean mentioned, I believe that the vendor, because they took it quite seriously, and we have to actually thank them. They were very cooperative, and like I said, they confirmed the problem, and they notified us that they are actually added a new test case to their test suite to actually detect this kind of attack. So hopefully going forward there shouldn't be any problems.
A follow-up then, so devices are certified by Z-Wave?
That's the business model that it works. Yeah, there's Z-Wave Alliance, which actually certifies the devices. And in order to get that certification, you have to pass through a set of tests. And this would be actually part of the test as well to make sure that devices wouldn't miss this. Any other questions?
Yes.
Yes, sir.
You should.
Yeah, please.
Yeah, please, do you want?
Are Z-Wave devices susceptible to jamming the ISM band?
Jamming is a problem with all RF devices. So
We have this problem right now here.
you can see that's
You see that this is the direct connection to our modem, and when I reset it, if you see when I reset it, it sends out a 40 packet. It is reset. It receives the first movement of the motion sensor, and then it can't. So the problem is that we don't have a reliable radio like Z-Wave chip, and we should look into it more.
You guys didn't find that there's a certain kind of
there are some timeouts. So, for example, there are ACK packets. If a packet is not acknowledged within a certain time, then the protocol won't go ahead. There's also the timeout on the nonce value. So if you get a nonce from a secure device like the lock, and if you don't send the response within a limited time, then it wouldn't accept, so the nonce just expires. So there are timeouts like that. But going back to your original question, the jamming, that's a problem with all RF devices. We didn't research the products available, but we think that actually, some of the products that we saw, without too much detailed research, we think that they actually might be susceptible to jamming. For example, if the motion sensor, this was actually the first attack idea that we had, but we moved on because we found a more interesting one. So if the motion sensor, for example, sends a packet to the siren that, hey, I've detected a movement, if at the same time, using ZForce, you start transmitting something, that packet would be lost. So the siren wouldn't see that coming through. So this can be worked around. It's not a protocol issue, but as a system, there can be workarounds. There can be like watchdog mechanisms to prevent things like that. So if the siren doesn't hear anything from the motion sensor within a certain time, then it will go off because there's something wrong. So there can be things like that, but it is susceptible to jamming. You're welcome. Other questions? Yes, sir. So for the replay attacks, for the things like the motion sensor which don't have the security, don't support the security class, replay attack is just like whatever you see, you replay it. There is no nonce, there is no encryption. For the secure devices, there is a nonce value, and that's a random number. So it has the Z-Wave modules, they have a pseudo-random number generator in hardware, and they use that to generate the nonce value. So the nonce values are all different. We did a little bit work on the random number generator, didn't spend too much time on it, but the numbers seem to be nonce values, so they only use once because they're quite random, and it's 8 bytes long as well. It also uses an IV, an initialization vector as well, and that's another 8 bytes. So these two together, you have 16 bytes with changes all the time. So it's quite resilient to replay attacks.
So was the nonce used as part of the actual key exchange?
Not as part of the key exchange, but in that sequence diagram that we saw, the last 3 steps. So every time that a device wants to send a secure or encrypted message to another device, those last 3 steps in that sequence diagram gets repeated. So the first one is the transmitting device sends a nonce request to the receiver, then the receiver replies with a nonce, and then the transmitter uses that nonce value to authenticate the packet and send it back.
The nonce value actually is used to calculate the MAC. So in MAC calculation, you include the nonce, and then you verify when you receive a packet, before decrypting it, you should verify the MAC value. And when you want to verify MAC value, you should have the same nonce value that you expect that your sender calculated the MAC with. So that's where the nonce value actually comes into play.
So just very maybe your back, if say it was just your length, say it is a bad idea, but if it was part of say the key exchange and there was kind of a timeout matching to see that we expect we saw the initialization, we had a kind of a race condition, we need to a few seconds or timeout actually get that response and it actually like at sometimes reassess and use a different nonce and make like a pure request difference between it. Actually it's more like a racing condition. We have a little bit more space, is that
It won't prevent this attack. There are two problems. One is the lack of use of a public, like a Diffie-Hellman protocol for based on public key cryptography. The second is lack of the authentication. If you want to implement something like that, it would be, some kind of obfuscation. Again, you can figure it out how it happens. Okay, thank you.
Right, thanks very much, everybody. If you could please just use your tags on the way out and provide us a feedback, that would be great. We appreciate it.